Hello, I'm Mingqi Han, and this is the video explanation for homework 10, question number 2. In this question, we are to find that for the following stochastic processes, the definitions of properties of it in the lecture notes and explain it in our own words. And the first one would be Weisson's stationary process, and it's right over here. So in the lecture note, we say that a real stochastic process as xt is stationary in White sense if its expected value is a constant and its autocorrelation depends on t1 minus t2 only, which basically means that you can see it as when the time, let's say this t time, where is it? This t changes by a or shifts by a value is is expected value and autocorrelation will change. Example would be, let's see from the previous question in the Poisson increment, or let's say the Poisson impulse, is constant is satisfies this White sense stationary because its expected value is a constant, and here this value, this autocorrelation value only depends on t1 minus t2 because this would always be a constant value. For the next one would be independent increment process, which is found in, let's see, in here. Independent increments implies uncorrelated increments, and uncorrelated increments is defined over here. Basically saying that xt1 minus xt2 and xt3 minus xt4 are not overlapping and independent. In which, yeah, for saying that is non-overlapping intervals. And an example of it would be, let's say, Poisson process is independent increment process. And for the third one, Markov process. Markov process is that the past has no influence on the statistics of the future when the present is known. So let's say that the future is only dependent on the current or the present value. So writing in another way would be x of m plus k at this time is only related to x of m, where m is the present time, k is the future, or the time plus the time to get to the future. And an example of Markov process would be a random walk would be a Markov process, because the next value, let's say right now you're walking to the location at +5, and each time you walk by one, increment or one location. So the next, or in the future, all the future's value depends on this current 5, because let's say the next one would not exceed 5 plus minus 1. So that's the Markov process. The normal process, saying that xt1, xt2, all the way to xtn are jointly normal for any n, any t1 to tn. And here is the function explaining the same thing over here. Let's see if I can find the, yeah, here. So this C is the ultimate covariance matrix, and this eta would be the expected matrix, and yeah, the entire thing just explains the normal process. And for the strict sense stationary, let's see if I can find it. Yeah, if on the topics of wide sense stationary process, we're saying that when the time shifts, its expected value is not changing. Its autocorrelation is not changing. And in the strict sense, we're saying that not only that two are not changing. When the time shifts, the entire statistics, or let's say is distribution function, is not changing. So here, the not shifted time of that distribution is the same as the shifted of that same distribution. And with that, we can say that strict sense implies wide sense stationary, because, well, this part with or without shifted, these their distribution function would be the same. And with that being the same, expected value and the autocorrelation would also just be the same. And that's it for the question for a strict sense. The next one would be white noise. Well, in the definition, it says that takes a bit to find out where it is. Where am I? Yeah. Here's the white noise. Yeah, definition, T is a zero mean white noise if this autocorrelation is equal to this function. So it's pretty much just defined on this average intensity. Other thing is just and any single value would be almost independent of itself, and at any different time, their value are uncorrelated. And the next one will be mean ergodic process, and it's basically means that for any process that with expect value, or let's say with everything, let's say that it has a large enough sample amount of samples, and for everything that this amount of samples added up, divided by added up is over here, divided by the amount of samples that it takes, is equal to the mean, is equals to its expected value. So we basically means that if we have let's say not a long amount of samples, or maybe just a few samples, we can still predict what is happening next, because the entire process is almost like revolving around the mean value, which is right over here. And the next one, martingale, would be the expectation of the next value, or the future values, is equal to the present value. So unlike the mean ergodic process, where every value revolves around, let's say, the same amount, the martingale value would be the amount of expectation of the next value is equal to the present value, which is the next one is dependent on the current one. So that's the difference between the mean ergodic and martingale. And for the equation, it's written like this. And that's everything for this question.